So on the last example, we used the power rule for the negative exponents, but we hadn't proved it yet. So let's prove that it works now by using the quotient rule. So what are we going to do? We're going to say, what is the function we have? Say the function we have, f of x, is x to say some negative number. Call it like negative n. So how are we going to... Well, n is positive, I guess. So I guess we're going to say that n is greater than 0, but we're going to rewrite it as negative n. We're going to write it as negative n. And then we want to use the limit definition. So let's just write out what the limit definition is. F of x plus h minus f of x over h with the limit as h approaches 0. So that's what we're going to use here. So let's go ahead and do that then. Well, what's the whole point of this anyway? The whole point of this anyway is that this is 1 over x to the n. So I think that's what we need to do, is we need to plug it in like that. So we need to have 1 over x plus h to the n minus 1 over x to the n over h with the limit as h approaches 0. And then we would need to cross multiply, I suppose. Have x to the n minus x plus h to the n over h over, not over h, over h times x plus h to the n times x to the n. Okay. So what if we did this now? What if we separated this? So it's the limit of all of this, right? So let's remember that this is the limit of all of this. So what if we now separated this, kind of like we did how for quotient rule, but we need to factor out a negative from the top. So I'm going to write negative 1 over x plus h to the n times x to the n. And then since we factored out this negative, we're going to flip this around, have this x plus h to the n minus x to the n over h. Because now what I'm seeing here is that when we take this derivative, look how that's the derivative. This right here is the derivative of x to the n. And we've already proven x to the n, because look, x to the n is a positive number. So this part of the function right here is just an x to the n, is legal. That we already proven the power rule for that. We've already proven the power rule for positive integers. We're just trying to prove it for negative integers. So we're actually going to use that fact. We're going to use that fact that this entire Pinck's expression here is just the derivative of x to the n, and n is positive. So we know when we take the derivative, we know how to do that. We know that that's n minus 1. No, we don't. We know that it's n times x to the n minus 1. That's what that entire Pinck expression is. And then what happens when we plug in h equals 0 for this first part? That's legal. So that's negative 1 over x plus 0 to the n times x to the n. X to the n times x to the n. So let's see. So let's cram all that together. So we have negative n, actually, times x to the n minus 1 over x to the n times x to the n. So that means you add the exponents, n plus n. So x to the 2n. Okay. Now we have x divided by x, same base. So now we can subtract the exponents. So that's negative n, x to the n minus 1 minus 2n, which is negative n times x to the negative n minus 1. And that's the final thing. So what did we just show? We just showed that when we try to take the derivative of this function right here, we get that f prime of x is equal to that. And see what that is. That's just like it is for the positive numbers. That negative n comes to the front, and then we have negative n minus 1. That's cool. I've never done that before. So what have we proven now? We've proven the power rule for the positive numbers, and we've proven the power rule for the positive integers, and we've proven the power rule for the negative integers. We've not proven the power rule for any of the numbers in between, any of the rational numbers or irrational numbers that are not integers. I mean, it works for that too, at least as far as I know. We just haven't proven it yet. But I'm sure we'll get there. That was a cool proof. That was neat.